Hi guys, it's Professor Stevens. I'm going to walk you through an example from 2.4, and this answer sheet is going to help us organize some values and try to interpret what they mean. So let's read the question first. It says a sample of 60 women is obtained and their heights in inches and pulse rates in beats per minute are measured. The linear correlation coefficient is 0.234, and the equation of the regression line is y hat equals 17.5 plus 0.85 times x, where x represents height. The mean of the 60 inches is 63.4 inches, and the mean of the 60 pulse rates is 75.6 beats per minute. When find the best predicted pulse rate of a woman who is 74 inches tall and use a significance level of alpha. Alright, so as we read through this, we can start to sort things out. I guess the easiest thing to sort out is that the sample size is 60, right? Pretty straightforward. Also, the alpha, which is our significance level, is 0.01. That's just a given. And then they gave us the regression line. The y-intercept would be 17.5. And the slope is 0.85. And then the mean of x, well, it says right here that x is representing height. Just like when we read the example, it said that the first variable was their height in inches, and typically the first variable mentioned will be the independent variable or the input variable, or sometimes we call it explanatory, or the predictor variable, and that would be your height. So we have a mean of the heights of 63.4. So x bar, the mean of the heights, would be 63.4, and that's a height in inches. And then for y bar, well, if the x represents height, what's the other variable? The other variable is pulse rate. And so the pulse rate average, the average pulse rate of those 60 women was, it's over here, 75.6, right? So we'll put in 75.6 right here. And that is beats per minute, pulse rate, beats per minute. All right. Then we have the Pearson linear correlation coefficients. The one that comes from our sample data is the one that we refer to as a test statistic, and we're really only interested in the strength of the linear correlation in determining whether or not we should allow ourselves to use this line to make predictions of someone's pulse rate based on their height. So we'll look at the linear correlation coefficient that was calculated from the data, and the number here is 0.234, as you can see. The linear correlation coefficient is 0.234, and we can put that right in here, and it's already positive. So if it had been negative, we would still write the positive here, just because you see the absolute value symbols around it, because it's just more important to us how close it is to 1 or -1. So we really care about how far away it is from 0, is another way of saying that. So we always look at the amount, not so much the sign, in determining strength. And then the critical value is going to be the one that we will compare our linear correlation coefficient to. We're going to use this to determine the strength, but we need something to compare it to. So that will be the critical value from the table. So going over to our formula packet, the fourth page is the linear correlation. You can see that it says if the absolute value of the test statistic is greater than the critical value, and then it says from the calculator, RTS is from the calculator, which is another way of saying, well, you calculate the test statistic, maybe you use a calculator or some form of a calculator like Excel or StatCrunch or whatever. So that actually, another way of saying that is that it comes from your data, just by, applying a certain formula. And then the critical value actually comes from the table. And this is a little hard to read. This copy's not so great, but it does say table A6 is the critical values of the Pearson correlation coefficient R. So critical value, right? So it's RCV. So we get the critical value from this table. We had 60 pieces of data, so the little n, sample size of 60, we want to be down here in this row. And then we have two significance levels we could go with. This problem told us to go with 0.01, so we'll be looking in this column on the end here in the row for 60, sample size 60. So our critical value for this will be 0.330. So let's go back to our page here. And 0.330, right, so is our test statistic greater than our critical value? No. It's the linear correlation from our data is weaker than the critical value we need to meet or exceed. Now, let's put this on the map here. Let's put the test statistic, I don't know, somewhere right around here. 0.234 is the test statistic. So I'll put that over here. And I'm also going to put an asterisk because that's the convention and something I'd like you to try to do throughout the semester whenever you're denoting a test statistic and the critical value that you're comparing it to, and there will be a lot of applications for that as we go through the semester. One way to differentiate which one is the one that came from your data is to use the asterisk or the star symbol. So this little star symbol indicates that the test statistic, the data, had a strength of 0.234. And the critical value we needed to meet or exceed as a positive absolute value is 0.330. So I'll put that right here because they're kind of close. 0.330. It doesn't have to be, whoa, what happened there? I need to go back down to a reasonable size here. 0.330. That's good enough for me, right? So that you could say is somewhere right in here. And if you're doing it with a pen, it's a little easier. You can just make like a little tick mark there or whatever so that you can show where it is. But that's your critical value. The test statistic is not closer to 1 than the critical value, so there is not a significantly strong linear correlation. So we'd say no. And before we get to the final question, which is to estimate the best possible estimate of y, which is pulse rate, we will also answer one other question. It says, about what percentage of the variation in y can be explained by x using this linear model? This choice of terminology, the way that this is worded, using the words what percentage of the variation in y can be explained by x, is the reason that sometimes x is referred to as the explanatory variable. And what we do is we take our linear correlation coefficient, 0.234, that came from the data, and we square that and turn it into a percentage to answer this question. So let's calculate that. I'm going to use Excel here. I'm going to move that down for the time being, and this is going to be our R, and then I'm going to do our R squared So I had 0.234 for R, and then R squared would be using the caret key for exponents. Remember, whenever you put an equal sign into a cell in Excel, in Microsoft Excel, whenever you start with an equal sign, it turns that cell into a calculator. And then I'm clicking on the cell where I've entered my linear correlation coefficient amount, cell column B, row 1, and I've clicked on that to refer to it rather than typing in 0.234. I can actually type in 0.234 and then raise it to the power of 2 and get my answer. Or if I want to be able to, like, every time I do an example like this, if I want to be able to just change this and have my R squared, if I want to just be able to change R and have R squared automatically recalculate itself, then I can use a relative formula. So I'm going to show you how to do the relative formula. So I started out with equals, and instead of typing 0.234, I referred to the cell, and I put the caret key and 2. And now if I do a different problem with a different linear correlation coefficient, you know, my R squared value will automatically recalculate. All right, now the other thing that you can do here is you can right click, format cells, and turn this into a percentage. So now that answers our question. 5.48% was the answer. So when you square 0.234 and turn that into a percentage, you get 5.48%. All right, so let's read this. It says, about what percentage of the variation in Y, in other words, and about what percentage of the variation in a person's, or specifically, these are samples of women. That's what it says up here, right? In a sample of 60 women, where their heights in inches are recorded and their pulse rates, and we're letting heights be X and pulse rates be Y. So about what percentage of the variation in a woman's pulse rate can be explained by her height in inches? All right, so I'll read that again. About what percentage of the variation in a woman's pulse rate in beats per minute can be explained by her height in inches using this linear model? What linear model, do you ask? This linear model. This equation is a model. It's a model for a woman's pulse rate based on her height. Okay, so the output is her pulse rate, and we're basing it on an input of her height if we use this model. Now, if we use this model, we'll be able to explain about 5.48% of the changes in a woman's pulse rate based on her height. Not a real good measurement there. Not too good. Not too great. Then we can also come over here and talk about what this means. Is there a significantly strong linear correlation? No, right? We already determined that our test statistic was not stronger than our critical value. So no, which means then we shouldn't use that line, that linear equation. We should not use that to make predictions. We would not be justified in doing so. So then what can we do to answer this question instead? Unfortunately, we just have to go with the next best thing. So the best point estimate will be the average pulse rate. Okay, so rather than plugging in a woman's height into the linear formula to get an estimated pulse rate, since we don't have a strong enough linear correlation, that wouldn't be a good thing to do. So instead, the next best thing is to use the average pulse rate, which was 75.6 beats per minute. So that's the final answer for this one, 75.6 beats per minute for that one. Okay, and then we do a similar example over here. very similar, but let's see how it turns out. It says a sample of 90 women is obtained and their heights in inches. It's exactly the same setup. The only difference is the values, right? So let's start to sort everything out. We've got a sample size of 90 this time. We're still going to use a significance level of 0.01, and we've got a different linear regression. We've got a y-intercept, so whenever there's no amount of height present, you would start at 18.4 beats per minute, and then for every increase of 1 inch in a woman's height, this is how much increase in the beats per minute you should see, the marginal change. The slope is 0.91. And that'll be times x. I don't know why I provided so much room here. It's clearly much more than I need. It's kind of awkward looking. So that's, you know, it's the hey man, that's the number was supposed to come with. Let's see. So the 0.91 is the coefficient of the x term. That's multiplying the x term. All right, so now we can also look at what's the average x. Well, again, x represents height, and the mean of the 90 heights is 62.9 inches. So 62.9 inches. And the average pulse rate is given as 75.6. So 75.6 beats per minute is the average pulse rate for these 90 women. The linear correlation coefficient, again, seems pretty low, 0.284. And the critical value, actually, before I go into critical value, let's calculate r squared real quick. 0.284 and then we have an answer of 8.07%. Okay, so this time it's doing a little better. Not great, but it is somewhat better. I don't know, 8.07%. And now the critical value we'll get out of this table, table A6, looking at a sample size of 90, but using the same significance level, we end up with 0.269. Okay, so again, we were in the sample size column N. We chose N equals 90, and then we're moving over to the 0.01 significance level. So we get that critical value of 0.269. Okay, now, is my test statistic stronger than the critical value? Yeah, it's higher, right? 0.284 is greater than 0.269. So this time my critical value is 0.269, and that's actually probably not in the best spot, but let me see if I can get it a little bit better. Somewhere around there. And then the test statistic is 0.284, right? So we've got the critical value there, and then the test statistic of 0.284. And I used my little star, but this time it's tiny. It's tiny, hard to see, so I didn't make it bigger. But so there's my 0.284 test statistic. So you could even do test statistic here if that seems better, just for the purposes of typing isn't working out so great. I don't even mind if you do this, but sometimes when you're filling in a graph, you'd rather just put a star than I don't know. Sometimes there's not a lot of space and you don't want to write too many characters because things start looking convoluted, but this is okay right here. So we have the test statistic is closer to 1 than the critical value. And in this example, we already had a positive test statistic, so we really didn't face the issue of, you know, considering a negative. So is there a significantly strong linear correlation? We say yes. And then what is the best point estimate of y for the given value of x? Well, this time, because we found a significant amount of linear correlation, and why is it significant this time? Because the critical value didn't change that much from the last example, but the sample size did. And so when you have access to more data, your benchmark is going to be much lower. So we had a much lower goal to reach in order to claim significant correlation based on the fact that we had a much larger sample. So yeah, we're justified this time in using the equation 0.91, or I'm sorry, 18.4 plus 0.91 times x. So we'll go ahead and put those values into our spreadsheet here. B sub 0, when you use the underscore in this way, it can kind of represent dropping the 0 down to a subscript because it's sometimes difficult when you're typing to make that look right. So B underscore 0 means B sub 0, or that's our y-intercept. In other words, initially at an amount of x equaling 0, so no inches of height. In theory, we should start out with at least 18.4 beats per minute. And then for each increase of 1 inch of height, our pulse rate should increase by 0.91 beats per minute for each increase of 1 inch. And we are going to use a certain number of inches, and then we'll use that number of inches and calculate the estimated pulse rate to go with that using this model. So which x value shall we use here? So let's look at this question again. It says, what is the best point estimate of y for the given value of x? So where was the value given? It says it was the given value of x. So it must have been given up here in the represented problem, right? So somewhere it's telling us, and it's that last sentence, it says, well, almost last sentence, it says, find the best predicted pulse rate of a woman who is 70 inches tall. Well, there's your specific value of x to put into the formula. So we're going to do this for 70 inches of height, and we're going to estimate what pulse rate this woman should have. So I'm going to do the y-intercept of 18.4 plus the slope of 0.91 times 70 inches. So I get an estimated pulse rate of 82.1 beats per minute. So I'm going to pull that back down in here. All right. So that's how we roll with linear regression. To summarize, if your test statistic, the linear correlation that is reported in the problem about your data, if that beats the critical value that you find in this table, then you say you can use the line. And if you can use the line, and you do use the line, you calculate by plugging in the value into the linear correlation line equation, and that'll be your final answer for the best predicted value, right? However, If you do not have a high enough strength to meet the critical value or exceed it, then you will not be able to use this equation to make a prediction. You will be stuck with the next best thing, which is the average of the y variable from your sample average. So I think I'm done. I don't think I need to tell you anything else for this type of example. Yep. So enjoy your the questions that go along with this. I think I'm using this as a pre-lecture assignment, so now you can try some similar examples. I can't figure out how to stop this. There we go. All right, ta-ta.